Okay, so now we look at another traversal algorithm called depth first search. Now, with breadth first search that we looked at in the previous video, we basically go breadth-wise in the sense that from one vertex we visit all its neighbors. And if you also notice in the examples that we explore the neighbors of node 1, which is at level 0, and then we explore the neighborhood of vertices at level 1. So only after finishing the vertices at level 1, we go to explore the neighborhood of vertices at level 2 and so on. So that's why it's called breadth first search. On the other hand, in depth first search, we start with one vertex and visit one of its neighbors and then go further down visiting one of its neighbors and so on. So we go as deep as possible until we cannot go any deep further, and then we back up. Okay, so this is the key difference between breadth first search and depth first search. So in breadth first search, we use a queue to keep track of the vertices that we need to explore for the neighborhood. Whereas in depth first search, we use a stack to keep track of the vertices that have been visited, that have been kind of just visited but neighborhood not explored and all the stuff. So we'll see the details as we proceed. Okay. So we are not going to keep track of the level numbers, but instead we are going to keep track of for each vertex a tuple indicating when did we visit the vertex, in the sense that when did we push the vertex to the stack and when we pop out the vertex from the stack. So a stack is also a data structure like a queue, but the difference between a stack and a queue is a stack operates in last in first out fashion, whereas a queue operates in first out fashion. So you could keep adding, pushing things to a stack, but what we remove from the stack is what we added, what we pushed the latest to the stack. So if I push 1 followed by 2 followed by 3 followed by 4, 5, then then 5 was the last thing that I pushed to the stack. So when I pop out the stack, 5 will come out of the stack, because what we push to the stack is considered to be what we push at the latest is considered to be the top of the stack. So when we pop, which means removing something from the stack, what's in the top of the stack comes out of the stack. Alright, so for each vertex we keep track of the push order and pop order. So to begin with, again we can start from some vertex. We'll follow the convention starting from the lower ID vertex. So one is push to the stack, and it's also called the root, of course. Then the one is the first vertex to be pushed to a stack, so its push order is 1. So now from 1 we can go to one of its neighbors. So we pick the lower ID neighbor that has not been yet visited or pushed to the stack. So 2 is the lower ID neighbor, so visit 2 for the first time. So we mark that edge as a tree edge, and 2 is now pushed to the stack. So 2 is now in the top of the stack. So we indicate the first vertex in the stack list is at the top of the stack. Now 2 is the second vertex to be pushed to the stack, so its push order is 2. Now from 2 you can go to either 4 or 7. You pick the lower ID neighbor, so you go to 4. 4 has not been yet visited, so that's a tree edge, and 4 is the third vertex to be pushed to the stack. So 4 is in the top of the stack. So from 4 you visit one of its neighbors, which are 3, 5 and 6. So let us visit 3, the lower ID neighbor. So 3 has not been visited yet, so marked as a tree edge, and its push order is 4. So you see, you keep going deep as possible, from 1 to 2 and then 2 to 4, now 4 to 3, and from 3 you can try to go anywhere else. So you can go to 5. Now this edge to 1 should be called a back edge, because 1 has been already visited. So similar to cross edge, this is called a back edge. So we will call the edge between 3 and 1 as a back edge, and that also indicates as a cycle. So similarly, in breadth first search, the presence of a cross edge indicates a cycle. So from 3, now we can go to 5. 5 is now the fifth vertex we push to the stack. So 5 is in the top of the stack. Now from 5 you try to go further down, so you can go to 6. So 6 is now pushed to the stack, it's on the top of the stack, and its push order is 6, labeled edge as 3 edge. I can not go anywhere else from 6, but this edge to between 6 and 4 should be called a back edge, because 4 has been already pushed to the stack. So 6 is the 6th vertex we pushed, and we cannot go anywhere else from 6, so it's time to pop out 6 from the stack. So you start with 1, went to 2, 4, 3, 5 and 6, so as deep as possible, and we cannot go anywhere else from 6, so we pop out 6 from the stack. So 6 is the first vertex to be popped out of the stack. So the top of the stack now has 5, 3, 4, 2, 1. So you kind of now from 5, which is in the top of the stack, try to go anywhere else, but you cannot go anywhere else. So we classify also now the edge between 5 and 4 as a back edge. Okay, so since 4 has been already visited, so pop 5 from the stack. So 5 is the second vertex to be popped out of the stack. So the top of the stack is 3. Now from 3 we cannot go anywhere else to a new vertex, and all the associated edges have been already classified. So it's time to pop out 3 from the stack. So 3 is the third vertex to be popped out of the stack. Now 4 is the next vertex to be popped out of the stack, and all the neighbors of 4 and the edges have been already classified. Now 2 is the next vertex that is to be popped out, so it takes a neighborhood of 2. So you see there's an edge to 7. This is a tree edge, and 7 has been already pushed, and now it's now pushed to the stack. It's now visited. So 7 is the 7th vertex to be visited, pushed to the stack. Now from 7 try to go now deep. So because 7 is now the top of the stack, you now try to go deep. Now this edge to 1 is a back edge, because 1 has been already visited, so I pop out 7 from the stack. So the stack has 2 and 1. So now we cannot go anywhere else from 2, so you pop out 2. So 2 is the 6th vertex to be popped out of the stack, because 7 is popped out earlier, that's a 5th vertex. So before 7, 4 was popped out as the 4th vertex. Now 7 is pushed and cannot go anywhere else from 7, so 7 is the 5th vertex to be popped out. So 2 cannot go anywhere else, so that's the 6th vertex to be popped out. So stack currently has 1 in it. Now 1, all the neighbors have been already visited, and the edges are classified, so you cannot go anywhere else from 1. So we mark its pop order as 7 and pop it out of the stack. So the stack kind of becomes empty as we do breadth first search. So vertex 1 is the 7th vertex to be popped out of the stack. Okay. Alright, so there are several applications of depth first search. One application is to decide whether a vertex is an articulation point or not. Now before we do that, let us look at depth first search on this graph. So let us say I start with vertex 1. So push vertex 1 to stack. So the push order for vertex 1 is 1. And from 1 you can go to 2, 8, 4, 2, 4, 8 and 11. So visit the lower ID neighbor. So you push 2 to the stack, mark its push order as 2, and label the edge from between 1 and 2 as a tree edge. So from 2 you can go to 3. So 3 is the third vertex we push to the stack. Mark the edge between 2 and 3 as a tree edge. And from 3 you can go to 4. 4 is now the fourth vertex we push to the stack. Mark that edge as a tree edge. Now from 4 we cannot go anywhere else. So label the edge between 4 and 1 as a back edge. Now pop out 4 from the stack. So 4 is the first vertex we popped out of the stack. So the top of the stack currently has 3 in it, and we can now go from 3 to 5. So 5 is the fifth vertex we push to a stack, and then from 5 you can go to 6. This is the sixth vertex we pushed. From 6 we can go to 7. That's the seventh vertex we push to the stack. Now from 7 we cannot go anywhere else deep to a new vertex. So you have to label now these edges to 5 and 3 as back edges. So you remove pop 7 from the stack, that's the second vertex we popped out of the stack. So you're back to 6. You cannot do anything else, so you pop out 6 from the stack, back to 4, sorry, back to 5. You cannot go anywhere else from 5, so pop it out of the stack. And then go to 3, you cannot go anywhere else from 3, so pop out 3 from the stack. Now from 2 we cannot go anywhere else from the stack, so pop out 2. So that's the sixth vertex we popped out of the stack. So now we are back to 1. So from 1 now we can go to 8, which is not yet visited, so label the edge as 8, vertex as 8, and that's a push order, and label mark the edge as tree edge. So from 8 you can go to 9, that's the ninth vertex we pushed to the stack. From 9 we can go to 11, that's the 10th vertex we pushed. And then from 11 we can go to 10, that is the 11th vertex we pushed. Now from 10 we cannot go anywhere else, so you pop out 10. So we already pushed and popped 7 vertices out of stack, so that's the 8th vertex to be popped out of the stack. Now you can also label the edge from 11 to 1 as a back edge. Now once you pop out 11, the queue has 9 in it. From 9 we cannot go, there is no edge to associate with 9. Now for 8 you have a back edge 10, which has been already classified, so we cannot do anything else at 8. So time to pop out 8 from the stack. This is the 10th vertex, and then the root 1 you have the 11th vertex. And then so basically you have visited and push and pop all the vertices. So you can put together the results of breadth depth first search and draw what is called a depth first search tree. And here I identified the internal nodes and then the leaf nodes. So for internal nodes you have at least one edge further down, and then for leaf nodes, that's the end. We cannot, leaf nodes don't have a child node, so you don't have any edge in the depth first search tree further down. So 4, 7 and 10 don't have any edge further down in the depth first search tree, so they're called leaf edges. So a leaf node. So let's stop with this.